back here. Yeah, so we're going to talk about all these different characteristics of CMOS circuits. First off, just a little review here. MOS transistors, we're going to kind of treat transistors like switches. We've kind of been doing that already to figure out what the logic function is. But it's important to realize that Nmos transistors, if you put a 0 voltage on the gate, then it's like a pipe. It's open and the pipe's blocked and there's no current flowing through it. So it's an open switch. If you put a 1 on it, it closes the switch. So the valve is open, so water will flow through it. But it turns out an Nmos transistor is good at passing a 0, but it's not so good at passing a 1. Now, I can explain that with a little picture here. We need to go back to our characteristic curves. So let's draw an Nmos transistor. I'm going to connect it like this. And let's do the first case. We put a 1, and here's the open. Let's say this was a capacitor, and it was charged to 1 volts, and I'm trying to make it go to 0 volts. So I'm trying to pass the 0 to there, right? I'm trying to discharge this, but effectively I'm trying to put a 0 through this switch. So let's look at the characteristic curves. What's happening in this situation? We have ID, we have VDS, and this is my gate and this is my source, the lowest voltage. So VGS is 1 volt here. So I'm just going to say, okay, I'm on this curve and VGS equals 1 volt. And initially, I had to go from 0 to 1. So let's say I went to 0 to 1 to turn it on. So when I was at 0, the drain source was over here, and the gate source, this is VGS equals 0, is just the x-axis. So I was at this point, and then what happened was this went up to 1 volt. So I jumped up right away to this point here. VGS is 1 volt. And then as this starts discharging it, I transition all the way down along here, right? I'm going down this curve. And eventually I get to this point where VDS is 0. So I discharge this capacitor to 0. No problem. So I passed that 0 through because the output went to 0 as well. What if I had the situation like this?
Would you mind going over that again?
So I have the gate source. I'm initially at 0 volts, and I'm at this point right here, right? Gate source is 0. There's no current going through it. So I'm on the x-axis. This is ID. I'm on the x-axis. There's no current. And VGS is equal 0. So I'm at this point. And then the gate goes to 1. So instantaneously, the gate goes to 1. I jump up to this new curve, VGS equals 1, right? This whole curve is VGS equals 1. But initially, I'm still at 1 volt. This is my drain here, right? VDS is still at 1 volt. And so I go to this point. And then I just start discharging this capacitor. It was originally at 1 volt, and it's going to discharge towards 0. So I go right along this curve, and there's nothing to prevent me. It'll discharge all the way to 0. This transistor will always be on, and it'll always discharge. There's nothing to stop it from discharging all the way to 0. Okay with that?
So is that transition very instantaneous?
Is it
like,
what?
Does it happen quickly, or does it happen?
Yeah, it happens very quickly. We're going to do a little calculation later today or next time. These things, what did I call you? What generation are you in? I said grandma was a millisecond. I'm or microseconds. I'm nanoseconds.
Pico.
And you're
We are pico.
Pico. This happens in picoseconds, okay? So this goes up and down like in picoseconds, because the capacitance that we just learned are very small. So the dotted is the discharge, capacitor discharge. This is with the voltage. What I'm showing you is the voltage. The voltage is going. The VDS, this is the VDS. I'm showing both voltage and current, actually. As I transition here, this is VDS is going down. That's this VDS. And the current jumps up. It's initially, there's a lot of current as it's discharging it. Eventually, there's no current once it's discharged. So yeah, it's the capacitor discharge, and we're showing the voltage and current. Pico, yeah, you're Pico. Colleen. Everybody okay now? Okay, let's look at a second scenario. Let's say I have this Nmos, and now I have a capacitor connected here. And this is connected to, say, 1 volt. This is Nmos. This is kind of related to your labs. This will be useful for your labs. And I'm initially at 0 volts here on the capacitor, and I'm trying to charge this up to 1 volt. Okay, I'm trying to make it go to 1 volt. And initially the transistor is turned off at 0, and then I go to 1. Okay, so let's draw what's happening here. So here's ID, and here's VDS. So, and now this is the source, right? Because this is the lowest voltage, and this is the drain, and this is the gate. So initially we're at VGS is 0, right? And VDS is 1. So we're initially at the same point, right? We have a large VDS of 1 volt, and we have a VGS of 0. And now this goes to 1 volt. So now the gate goes up to 1 volt. So the gate source voltage goes up to 1 volt. So here's our curve again. This is VGS equals 1 volt. So we jumped right up to this point. Follow me, right? And now current flows, and we start charging this up. Now, instead of discharging it, it's starting to charge towards 1 volt. But as we charge up here, notice this source voltage is changing. So VGS changes in this situation. Over here, we always had the same VGS, so we just stayed on this curve. But now as the source increases, the gate to source voltage, this voltage across here, is decreasing, right? This is at 1 volt, but now as we charge this up. So instead of staying on this one curve, we're actually going to move to different curves. So the drain source voltage is going to go down, so we're still going this direction, but we're also jumping to a new curve. So we're going to go to this point next. So instead of going right along that one line, we're kind of trajectory is like this. And if I were to draw these curves, I'll draw a few of them. We're going to kind of go like this. And the question is, are we going to get to 0 volts? Well, the answer is no, because this transistor has a VT. Let's say the VT is 0.2 volts, which is a typical value, 200 millivolts. Then what happens is, as this gets up to, like, in this case, 0.8 volts, the gate source voltage is going to become 0.2 volts, and this transistor is going to turn off. So in fact, if you look at this trajectory, it will stop right here at VT. The drain source voltage will be VT. So the highest this can get is 0.8 volts. It can't go all the way to 1 volt. And that's bad news. That means when I tried to pass this 1 volt through there, I didn't get up to 1 volt. So it wasn't very good at passing a one. So the Nmos, it's good at passing a 0. It's not good at passing a 1. But fortunately, we have PMOS, and the PMOS are the opposite. The PMOS are good at passing the 1 and not good at passing the 0. So we got to use them together to get our signals through our circuits.
Professor.
Yep.
I don't know if maybe I'm misreading this, but it kind of looks like on the one on the right that you're also trying to pass 1.
On the right?
Yeah.
No, it started at 1, but I'm trying to force it to 0. I'm discharging it to 0. So this is my 0. I'm trying to force this to 0. Here it's 1, and I'm trying to force it to 1.
Oh, I see. Okay. I understand. I was looking at the input instead.
Yeah, it's not the gate, it's the source or the drain, whichever. Anyway, that's kind of a little tricky concept, but yeah, that's important to understand. You'll use that for your lab. So back to our slide. So that's where this all comes from. This Nmos was good at passing the 0. but not good at passing the 1. And for PMOS, when the 1 is on the gate, it's closed, there's no current. When the 0 is on the gate, it's good at passing the 1, not good at passing the 0. And thankfully, they work the opposite way. So if we put them together, and that's what we're doing. Like when we make an inverter, when we make our little inverter here, that's what we did. We said, oh, when this went from 0 to 1 to 0, we got nice clean signals that went like that, inverted, because when it was 0 here, this was forcing it to 1. It was passing a good 1 through the PMOS, not the Nmos. And when this was 1, that went to a 0. And now we had the Nmos. It was good at passing the 0. So we used the P for making the 1s, and we use the N for making the 0s go through. Hopefully that makes sense.
I have a question about the characteristic curve.
Oh yeah.
So eventually, so you said if we so eventually you want the VDS to discharge to close to 0,
We want VDS,
right?
both these cases, we want VDS to go to 0. But in this case, because the drain was connected to 1 volt, it would try to force us to 1 volt. In this case, it forces it to 0.
So that means you want the VDS to go to the
To 0.
triode region, right? So
Well, no, we
which
want it
is-
to go to cutoff. We want it to go right down there. That's called cutoff.
oh, okay.
Anything along
Oh.
this x-axis is really called cutoff.
Oh, okay.
Okay.
Okay, just want to clarify. Thank you.
This is a picture of an inverter. This is our symbol for our inverter, and we already talked about this. When the input is a 0 on the gate of the inverter, the Nmos is on, it forces the output, or sorry, the PMOS is, is this picture wrong? I just noticed that this is backwards. Oh, sorry, it's going this direction. Okay, so when the input is 1, the Nmos is closed and the output goes to 0, right? And when the input is 0, the PMOS is closed and the output goes to 1. Yeah. In a CMOS circuit, you get rail to rail swing. That means because the PMOS is good at the 1s, you go all the way to VDD, and the Nmos is good at 0s, you go all the way to 0. Some other characteristics, it has high input impedance. So you're looking into this gate. I mean, there's some capacitance, but DC wise, there's very little current. So it's super high input impedance. This input is in giga ohms. DC input is like tens of giga ohms typically, but it's more than a giga ohm. And the output, depending on how much current it can be relatively low. So that's a good characteristic. And we can draw this DC transfer curve, which shows V in on the bottom and V out on the top, right? I don't know if you might have done transfer curves when you took electronics 1, but all this is saying is that when you're down here, V in is low. That was the situation here. V out is at VDD. It's all the way to VDD. And then as V in increases, eventually at some point, the PMOS starts turning off and the Nmos starts turning on. So this starts opening and this starts closing. And there's a point here in the middle where they're both on, but you're sort of transitioning. And then as you keep increasing V in, at some point, the PMOS opens and the Nmos closes and the output looks like 0. This region in here is kind of bad news. We don't want to operate in this region because it's kind of like an undefined voltage. Like we want to have logic voltages we want near VDD and ground. We don't want in between voltages. So we wanted to transition through this very quickly. And another thing that's not nice about this region is if you looked at the current going on here, when they're both on, there can be a short circuit current between them. So you kind of, if you were to plot the current, it would look something like this. There's no current when you're at VDD or 0. In between, there can be this short circuit current. We're not going to do too many calculations, but your simulations will show this, but we don't like that region at all. So we want to transition through there. Unfortunately, because our transistors switch so fast, we usually, when we're going from high to low, you don't see, this doesn't spend much time in this region, so we don't get a lot of current. Anyway, that's an ideal CMOS inverter, okay? Would look something like this with a very fast transition. And for symmetry, we usually make the PMOS bigger than the Nmos for older technology. Newer technologies are kind of similar in terms of mobility. So may I have a question?
Yeah. So I wanted to ask does that mean that if we lower the capacitance, we do two things? So we can increase like the maximum clock speed of the chip, but we also reduce power draw because we reduce the time
That's
in that
right.
region?
Yeah, last day we were saying we want to reduce that capacitance. And by the way, we just calculated this. Where'd it go? This capacitance is related to the width and the length. So if we make this length smaller, we'll lower the capacitance. And it turns out the current, which we calculate here, is really inversely related to the length. So if we make the length smaller, the current will go up. So smaller length means smaller capacitance and less and more current, which means faster and lower power.